Hello, my name is Christina and today I'll be talking about my physics lab 3. So the purpose of the lab is to, for the first part, estimate the mass of the black hole, and for the second part, determine what initial velocity my ship must have when it leaves the surface of the planet. The predicted motion will be demonstrated with a hypothetical computational model in GlowScript. So some fundamental principles we'll be talking about is the momentum principle and Newton's second law. We will apply these concepts to the lab further into the video, but in summary, we'll derive F equals ma into a formula that has both parallel and perpendicular components with momentum as one of its variables. For the second part of this experiment, we'll apply Newton's law of universal gravitational force. This will help us set up the model. So some potential errors for part 1, because we are given multiple masses of the black hole with each iteration, we will take the average of these values, which will leave room for error. For part 2, because we have to determine the initial velocity of the spaceship by guessing and checking, this could affect the accuracy of the data. So here's a preview of the main results. So here's what the pathway of both parts look like in GlowScript. As you can see, the star orbits the black hole in a circular motion, and we're able to compute the mass from this motion. This shows the motion of both the planet and spaceship. We are able to check when, the other graph, this shows the motion of both the planet and spaceship, and we are able to check which initial velocity will cause the spaceship to crash into the planet or get sucked by the black hole. So the principles we'll be talking about that I'll be going further into, we're able to calculate the gravitational force between two objects. Since Fnet is the gravitational force between star and the black hole, we can use this Fnet to then solve for mass. This force is what occurs between two objects in space, so that's why we're using that principle. And then we're using the momentum principle to, since we're given velocity, we can use the momentum principle and other derivations of this formula to calculate the change of, or the rate of change of momentum, and we can predict the motion of the planet and spaceship theoretically. So for part 1, the system is the star and the surroundings is the black hole, and they exert a force on each other. For part 2, the system is both the starship and planet, as we're finding the net force on these two objects in part 2, and the surroundings are dependent on the system being observed. So for example, if we're looking at the Fnet on the planet, then the spaceship and black hole are the surroundings. So here is the initial conditions for part 1. So for the lines of code, I adjusted my code accordingly so that it would demonstrate the star's orbit around the black hole. To find the change in momentum, I set it equal to the change of velocity times the mass of the star with the newfound delta p. To find the rate of change of momentum, I divided delta p with delta t and set this equal to Fnet, since we're in outer space and we can assume the gravitational force between the two objects is the only force acting upon the system. To find both parallel and perpendicular components of Fnet, we calculated the parallel component with the following formula and subtracted the newfound value from Fnet to get the perpendicular component. And then here's the other lines of code that I forgot to show, but here it is. So here are the initial conditions for part 2, both the program itself and the planet and spaceship. So for the lines of code, I adjusted my code accordingly so that it would demonstrate the planet's orbit around the black hole and the spaceship's motion. To find the overall net force acting upon the planet and spaceship, I first found out the distance between the spaceship and its surroundings. Then I found the magnitude of this, or the spaceship and its surroundings and the planet and its surroundings. Then I found the magnitude of this distance by using the following formula. Afterwards, I used these two newfound values and plugged them into the formula associated with Newton's law of universal gravitational force for the overall gravitational force on the system, which in this case would be either the spaceship or planet. Finally, I summed the two forces acting on the system to find the net force acting on the system for both the planet and spaceship respectively. So unlike this experiment, or I guess there's no experimental model, to compare the computational model to, so I'll skip this portion. And then now we're on to discussion. So technically, if we consider the mathematical relationship between Fnet and the rate of change of momentum, they're technically the same. But if we look into how we calculate Fnet compared to momentum, calculating Fnet involves acceleration, whereas calculating momentum involves velocity, and this makes it easier to calculate the rate of change of momentum. So the other question, which is like the what does it mean question, unfortunately I was unable to find the speed of the spaceship that simulates the this scenario, but I assume the speed I need to obtain for the x direction will have to be a lower velocity than the speed in the y direction, so that the spaceship can make a circular motion and not go in a horizontal pathway. The velocity in the y direction cannot be the same as the original speed, because this will cause the spaceship to crash into the planet potentially. So we need to we need to get a slightly different speed, and the velocity in the y direction shouldn't be too much greater than the x direction, otherwise it will fly further outward away from the gravitational pull of the black hole. So for my conclusions, here is a conclusion slide to sum everything up. Thank you so much for listening. Bye.